Perfect. Hi, folks. Welcome to our webinar today on interconnection and the Celtic Interconnector. My name is Conor Ryan. I'm the Secretary for the CIGRE Ireland NGN, and I'll be your chairperson for today. This is a collaborative event between the Irish and French NGNs. We thought the Celtic Interconnector would be a fitting topic, given that Ireland's only link currently to the power system is through Great Britain. So definitely it's a project that will be developing in the future, and it'll be very interesting to see how it plays out to connect both Ireland and France's power systems. As a summary just of the table of contents for today, we'll start with an intro to the Irish NGN by myself. Then I'll hand over to Nicolas Gadax from the French NGN, who will run through kind of their setup. We have 4 speakers lined up for today. So as it's a collaborative event, we have 2 from the Irish NGN and 2 from the French NGN. Thomas Whiteley will be presenting on interconnection infrastructure and asset management on the East-West Interconnector, or EWIC, which is the existing interconnector that we have between Ireland and Great Britain. Speaker 2 is Gianni Bakos, who will be presenting on the advantages and challenges of HVDC links, which will be used for the Celtic Interconnector. Speaker 3 is Adrian Coughlin, who will be presenting on HVDC converter technology that will be used for the Celtic Interconnector. And then speaker 4 is Yanis Corlu, who will be presenting on the HVDC cable link. We have a Slido code and a Slido link that I believe was sent out in the emails, and our code is #CIGRENGN. So you can upload your questions there if you have any. We won't be doing questions between presentations. We will have time for a panel discussion and Q&A at the end. So just as an overview, I suppose, of what CIGRE is a worldwide organization that develops the exchange of engineering knowledge in the power system industry. If you're not a member of it, anyone on this call or at this webinar, I'd advise you join up. It's a very good community with over 15,000 members, 60 national committees, and 1,250 member organizations. And it's very good if you need resources or any tools that are involved in the power system industry. It's very good to build up your knowledge and experience. The CIGRE NGN, then, our next generation network, is an organization which specifically allows young professionals to develop their knowledge in the power system industry through a number of ways, essentially industry related events. For example, the webinar we're having today, site visits. Obviously they're not happening much with COVID these days, but hopefully we'll get them in soon in the future. It provides good networking opportunities and a good platform where young engineers or even early career professionals can share their ideas and interact with industry experts. For example, we have many presentation competitions that people can put forward the names for. And it also gives you good look-ins to CIGRE working groups and technical events. Just on the Irish NGN then itself, we formed in 2018. We have a steady active membership base of 88 members to date, but we're hoping to hit 100 by the end of the year. We've hit many major milestones since formation. We've done a lot of events. So we've even made a constitution lately this year. Our big focus really, I suppose you can see up here, is mainly where EirGrid and ESB makes up a good bulk of the membership, and we're hoping to expand out into universities, into other companies. So please feel free to spread the word about us. It doesn't have to be just limited to those companies. With regards to our committee, the chairperson is Conor Mulholland, with the vice chair, Keith Keeley. And then our secretary is myself. I won't go into too much details on the rest of the names, but as you can see from the top right, we have a very diverse committee in that they're all from different backgrounds and different companies and universities, which gives us a good diverse expertise and well-rounded background for the committee for our events. Previous events and upcoming events for 2021. So in December 2020, we did a Providing Power During the Pandemic event, which is a webinar on how the Irish power system reacted to the COVID pandemic, which is very interesting, given it's such a once-in-a-lifetime kind of situation. Earlier this year in May, we did an event on application of machine learning techniques in the power systems industry. Currently, of course, we're having our Interconnection and Celtic Interconnector event. And then around late November or December, we'll be having our NGN event week, where we'll be planning out a number of activities, including a presentation competition, a Women in Engineering event, and hopefully more things to come. I'll hand you over now to Nicolas Gadax of the French NGN, and he will go through the work they've been doing so far to date.
Thank you, Connor. Before we start with the first speaker, a few words on the French NGN. Okay. So first of all, we have 113 members. Among them are 50 individual 1 members of CIGRE and 63 individual 2 members. And we have a great student community with 210 students currently registered. Our committee is composed of 10 active members, among which more than 6 companies are represented. So it's more or less the same organization as the Irish person and people responsible for different positions in the organization. In terms of events, 2020-21 were mainly online event years due to the current situation. One of the events we organized was a conference with a thesis introduction by Nicolas Mandulet, with a great conclusion by Michel Augonnet, the president of CIGRE. We also like to organize webinar for students on which we introduce professions of the high voltage sector for students who don't know how to orient in the high voltage sector or want to have more information, with very diverse speakers from different companies and different positions. We had 2 great opportunities as well with the GYECC, the Global Youth Engineering Climate Conference, on which we were able to introduce SF6 alternatives in high voltage applications. And we were part also of the NGN Forum in Paris for the centenarial session. One of the highlights of the NGN International event being the interview of Michel Augonnet, for example. We are trying to make more and more in-person events as the situation recovers. We will have one of them with the National French Committee for the 100 years of CIGRE. We also have a joint event planned with the Women in Energy event, the Women in Energy community, and we will organize other webinars for students, as well as a contest with a technical paper challenge and a presentation in 2022, more information to come on that. So now it's time to start with our first speaker. Connor, I let you introduce our first presenter today. Thank you very much.
Yeah, good stuff. Thank you for that, Nicholas. Oops, I think I shut that down there. Back on again. I'll move over now onto the first speaker today, which is Thomas Whiteley. So Thomas is the lead cable engineer on the AirGrid asset management team for the East-West Interconnector EWIC, and he'll be presenting on interconnector infrastructure and asset management of EWIC.
Thanks, Connor. Let's see if I can control these slides. Great. So as Connor said, I am the lead cable engineer for the asset management team for EWIC. I've been in the role for just under 2 years now. I'm going to give a brief overview of EWIC infrastructure, and then I'm just going to give an idea of what systems we use to manage the asset, and a quick overview of some of the projects we're involved in as well. So the cable portion of the asset is 262 kilometres in length. It runs from Portan in County Meath to Shotton in Wales. It makes landfall at Rush Beach in North Dublin and in Prestatyn in Wales. We have converter stations in both Portan and Shotton, and then as well as that, we have a cable spares facility in Liverpool, which we mobilise from in the event of a repair operation. So EWIC connects the power grids of Ireland and Great Britain, and it has a power rating of 500 megawatts. Shown here is a converter station, so they're quite similar on both sides of Ireland and Wales. We can see here our valve hall, we have our spare transformer, we've a fully equipped on-site spares facility, we have a redundant systems building, we've enhanced physical security system, which is quite new, and we have our black start facility in the form of a diesel standby generator. Just to run through some of the cable spec, our onshore cable, we have 2 200 kilovolt HVDC lightband cables situated from the Portan converter station to where it reaches the water at Rush North Beach. This is 44.5 kilometers of polyethylene aluminium cable, and it's installed in plastic ducts about 900 millimeters below the ground. Similarly, when we get to Wales, we have two 200 kilovolts HVDC cables, which goes from Barclay Beach to Shotton converter stations. We have 30 kilometers of this cable of the same polyethylene aluminium cable, and it's installed similarly to above with the plastic ducts about 900 millimeters below ground. From there, we then have three 400 kilovolt aluminium HVAC cables installed between Shotton converter station and the Conaskey substation, and this section of cable is installed direct buried. And we then have three 400 kilovolts copper HVDC cable solution for a river crossing section of the cable route across the River Dee. And these are installed in ducts filled with bentonite. And we have an additional spare ducts installed there also. So for the offshore portion of the cable, we have 200 kilovolt HVDC cables for the 186 kilometers of the route. These are spliced at Barclay Beach, which is the Wales side, and at Rush Beach in Ireland. And there's a transition joint pit at each location. These are bundled together along the seabed, and they're buried approximately 1.5 meters to 3 meters. And protection of this cable is a combination of rock dumping, mechanic rock cutting, trench cutting, vertical injection, and various crossing point protection mattresses. So as well as the power cable asset, we also run a fiber optic cable. So this runs along the HVDC power cable route, and it's installed in polyethylene ducts between the two land power cables and between the HVAC land cables also. So some of these fibers are leased externally, but for our own use, we use them for communication between the converter stations, and also we use them for temperature monitoring with our distributed temperature monitoring system, or our DTS system. So this system is based on optical time domain reflectometry. It was installed by Sensa in 2012, and at its time was state of the art. We've recently been experiencing some small issues, so we're in the very early stages of looking into a new system for this to upgrade it. And the setup we have at the moment, we have two systems in Portan and one in Shotton, and both of them monitor the entirety of the land cable route on both sides. And our one at Portan has coverage of 25 kilometers of subsea cable, and at Shotton we have 20 kilometers of subsea cable. So we're hoping to improve that going forward. And as I mentioned before, we also have a cable spares facility in Liverpool. So this whole facility is maintained in a state of readiness by our M&R team. It's climate controlled. I think we have approximately 10 kilometers of cable length ready to go at a moment's notice. And in the event we do need to mobilize, we will generally mobilize probably 3 times, that's what I have there, sorry, 3 times the water depth at the fault location. So in terms of how we manage the asset, the ISO 55001 is kind of our guiding principles, and how we try to, it's a standard we try to live and breathe within the team, and we do find it very, very good. It's a best practice framework for how we proactively manage the life cycle of the strategic assets. It gives us guiding principles. In terms of how we use it every day, I suppose we have documents such as our strategic asset management plan, which gives us our objectives and our goals for the year. We have a policy which guides a lot of our decision making. It determines how we manage changes within the team or externally. And we schedule critical activities through this system as well, such as performance management reviews and audits. And as well as that, it sets out a framework for how to manage risk. Obviously, CIGRE is an extremely risk-averse organization. So to have something which helps us manage that is obviously always welcome. So in terms of how we manage risk within the team, we carry out many risk reviews throughout the year, and these go to our government risk and compliance function within CIGRE. We have controls and mitigations for each risk, and our governance risk and compliance team will determine whether they feel these controls and mitigations are adequate. And if not, we'll obviously come back and revise. And this is a constantly evolving process. So examples of how we've been managing risk over the last while, we've increased our cable monitoring. We do marine surveys to assess the seabed conditions and the buried conditions of the cable. And we've also recently carried out a cable spares relocation project, which I'll touch on later as well. So the primary risks to the asset from a cable perspective at least are a land cable fault or a marine cable fault. A land cable fault can be something as simple as a contractor working in the vicinity of the cable who possibly isn't aware of its presence, or perhaps doesn't know it's there, but isn't aware of safe working practices in the vicinity of this asset. A marine cable fault could be something as simple as an anchor dragging or a trawler ship coming through and just not being aware of the asset. So the controls and mitigations we have in place for land cable faults, as I was saying before, we have robust cable buried protection systems. We have the distributed temperature sensing systems. We do fortnightly cable monitoring surveys in the form of a root drive, and we take EMF measurements. In terms of how we manage contractors possibly working in, near the cable, we have dial before you dig systems where contractors would log in and just log any work that they have that are going to be near the cable, and they'll be given guidelines of how to work in the area. And as well as this, we try to be proactive in tackling this kind of issue, in that we run contractor and council awareness workshops. Additionally, then we have a new GIS cable asset management system in which we log any incident reports. We have up-to-date as-bills, and anything we need up-to-date that's cable related will be included here. For marine cable faults, again, we have robust cable buried protection. We carry out comprehensive marine surveys, which I'm going to touch off in a little while. For a member of all relevant mapping associations, we have automatic shipping identification services, which means that we know how much shipping traffic is going to be passing over Ewick and the size of the ships, and again, that makes them aware of what assets they're crossing over as well. For any marine related projects, we have a marine liaison officer employed, and again, we have our distributed temperature monitoring system, which monitors the temperature on the cable for us. So in the event of a fault, cable fault, which thankfully hasn't happened in the lifetime of Ewick to date, we have a turnkey emergency repair contract, NKT. So this covers both land and marine. They keep their equipment in a state of readiness for us, as well as a mobilization vessel. We have a comprehensive preparedness plan, which covers all kinds of scenarios and sets out who takes what actions in the event of a possible land or marine fault, whether it's near shore or offshore. All scenarios covered, and we have guaranteed repair response times as part of this contract. So in terms of what kind of projects we work on, as I touched on earlier, we do marine surveys on a regular basis. This is to assess the seabed conditions and to assess the buried condition of the cable. So we carried one out in 2015, and this was followed up by a geophysical survey in 2019. This would have taken the form of a multi-beam echo sounders and side scan sonars to assess the burial condition of the cable, and any changes to the cable's current protection and environmental conditions were noted. The good news was that cable protection, which had previously been put in place, remained unchanged, but there was cable exposure identified. So this left us, we were presented with several options of whether to go down the route of pre-burial by means of trenching or jetting, concrete mattressing, or potential rock placement. So through a lot of planning, in December 2020, we undertook a project whereby 292 precision rock placement units were strategically placed along the cable route in 2-ton and 4-ton units, which covered our exposure and mitigated the issue. These came in the form of both fronded and unfronded. So some of these units have the rope-like material from the top, which when on the seabed will raise up and will mimic seaweed in a certain way, and will encourage increased sediment deposition, which will ideally give the asset additional protection. Another project which we worked on recently was the cable spare relocation project. This and the last one were both carried out during COVID, so we're quite proud of them, and they were both considered quite a success. This one involved mobilizing strategic lengths, 11-meter sections of land cables to both the converter stations at Shotton and Portan, which meant that in the case of the land cable fault, we were able to mobilize quicker and reduce any response times to a fault. This was particularly important leading into Brexit, so it was a project we were delighted to get done. And that's it for me. Conor, I'll hand that back to you. Thanks very much.
Yeah, lovely. Cheers, Thomas. That was really good, very interesting stuff. Definitely, it's interesting hearing how such a big cable going on the sea can be maintained somehow. It's quite a task.
It's an evolving field.
Yeah, I'll be passing on now to Gianni Bakos, who is a research engineer in the Control and Dispatch sub-program of Architecture and Systems program at CIGRE Institute in France. And Gianni will be presenting on the advantages and challenges of HVDC links such as the Celtic Interconnector.
So thank you for having me for this presentation. As Connor said, I'll be presenting the advantages and challenges of HVDC links, where you know that the main advantages are about empty DC links, but for this link, let's talk about HVDC ones. Maybe I cannot control the screen. I don't know. Yeah, now it's good. Okay, so first let's talk about the choice between AC and DC link. Why did we choose the DC link for the Celtic Interconnector? First, in the end, let's go back a little bit in the time. In the end of 19th century, there was a war between the AC and DC parties of current transmission. So yeah, so AC was chosen because we had it had many advantages, like some devices like transformers were existing in the 19th century to help change the AC voltage for power transmission. Like for the same amount of power, if you want to transmit it to a longer distance, we need to increase voltage so that we have lower current transmitting in the lines. And by this, we mean having lower losses. This was an advantage of the AC links. Then AC protection devices like circuit breakers needed less effort to open circuit than DC devices. At the other side, DC was at that period of time, I mean at 19th century, DC was not convenient for long distance power transmission. We didn't have high voltage DC because we didn't have power electronics at that time. DC was used for, like for example, direct current machines. So let's talk here about the Celtic Interconnector in particular. What if AC cable transmission was used instead of DC? So to tackle this question, let's look about the graph on the left side of the slide. This graph shows the cable length in kilometers compared to maximum transmissible power in megawatts. In this graph, you can see that for each parameter of voltage line, like here in for 225 kilovolts or for 400 kilovolts, you have some constraints, limitations that are existing due to maximum current and maximum voltage. For maximum current, you have the lines in black. For maximum voltage, you have the lines in red. So the current constraints, as you see here in black graphs, in black curves, they impose the most constraints and most limitations on the power system transmission. So like for 225 kilovolt cable, if you want to transmit it, if we have a 100 kilometer cable, the maximum transmissible power through this cable will be 100 megawatts. Same, for example, if we take the example of 400 kilovolts cable, for a 60 kilometers cable, maximum transmissible power will be 200 megawatts. So if you dig into the project, the Celtic Interconnector project, some key numbers of the project are that we have 500 kilometers underwater cable length, not talking also about the onshore cables. And we want a total power transmission capability of 700 megawatts. So clearly, it is clear here that AC transmission cannot be used for this project. So it's not only about technical feasibility of AC transmission, it's also about cost efficiency of HVDC transmission. So compared to HVAC links, HV stands for high voltage. Compared to HVAC links, HVDC has more DC terminal cost, as you can see in this graph, comparing cost relatively to distance, cost of cable transmission relatively to distance. So with DC terminal cost is much higher than AC terminal costs. So it is due to power converter stations. However, we have lower variable costs in DC transmission. They are due to lower transmission losses. We have no capacitive current, no skin effect in HVDC transmission. All this creates a break-even distance. You can see it here in the purple color or pink color, maybe. So this break-even distance is created once we have total AC cost depassing or higher than total DC cost. So for overhead lines, this distance is about 400 kilometers. For cable transmission, and this is astonishing, for cable transmission, it is about 50 kilometers. So at 50 kilometers, you'll have the total DC cost is much lower than total AC cost transmission. So for Celtic Interconnector, for 500 kilometers, you can clearly see what is more cost efficient. So let's in this slide summarize a little bit the advantages of HVDC versus HVAC and tackle also some challenges. So yeah, you have technical feasibility for long distance power transmission. You also have cost efficiency of HVDC due partially to lower losses in the transmission. You also have faster control thanks to the usage of power electronics that allow faster control. We have also added flexibility through HVDC because we can control power flow more or less as we can compared to AC system where power flow is a consequence of the system. We have also added control options to decouple disturbances between AC systems, or we can talk about disturbance mitigation. And also HVDC can provide ancillary services to enhance system stability. Finally, HVDC can connect to asynchronous AC grids, which is not possible with HVAC links. So all these advantages have on the other side present some challenges for HVDC. We need to develop new protection system devices like circuit breakers proper to HVDC that are not the same as HVDC protection devices. And here at Supergrid Institute, we have a team working on this part of the problem. Also, as I said earlier, we have more expenses coming before the operations, just like for DC terminal costs. It's called CapEx, capital expenditure of the system. So these expenses are higher for HVDC than for HVAC. We need to integrate HVDC in existing AC systems. So we will have a hybrid AC-DC system. So all this requires proper control of HVDC links, including proper filtering of HVDC links. Also, new studies show that, more or less new studies show that power electronics can have an effect, sometimes bad effect on power system stability. These power electronics exist only because of HVDC connection that needs them and requires them to be feasible technically. DC penetration ratio can also affect power system stability. And in the end, I want to talk about two things. Now that we have an AC and a DC system, a hybrid system, all this can be summarized, all the challenges of HVDC integration can be summarized in AC-DC interaction. We need to tackle this problem of AC-DC interaction. This is particularly the topic of my thesis in Supergrid Institute, in the team that works on control and dispatch of power grids. And we still need some return of experience. We don't have a big return of experience such as for AC systems. So we still need some return of experience for HVDC systems to make sure the system works correctly. Now we don't have problems, but big return of experience is welcome. Just to finish, I want to talk about a stability issue that cannot happen in Celtic Interconnector because we don't have AC line connecting France to Ireland. But it's interesting to look how HVDC can influence in a good manner or in a bad manner the power system. So here you have an issue. The concert connection is the INELF connection connecting France here to Spain here. So as you see, there was a more or less 1.2 gigawatt of power flowing through AC lines from Spain to France, but the line was opened due to a fault. And after that, all the power flowing through AC lines was transited through DC lines that moved from the power flowing through them moved from 500 megawatts to like 1 gigawatt. All this was thanks to the control of the HVDC links, the ADC controller. However, this issue that happened only between France and Spain created undamped oscillations appearing more widely in the big continental Europe grid. They appeared in Denmark, in Germany, in Turkey. They occurred inter-area oscillations. Their frequency is about 0.15 hertz. So the ENSOE report that studied the issue at the time said that the HVDC influence and PSS settings across CE systems should be investigated. Just I wanted to show this example to put an emphasis on the importance of proper control of HVDC links to ensure we have a proper system and a reliable system. And to finish, I'd like to say something a little bit interesting. So what's better, HVAC or HVDC? Having the challenges and having the technical advantages. So I think they're better together. Thank you.
Yeah, perfect. Thanks a million for that, Johnny. It was very, very good presentation. Extremely interesting, especially seeing kind of how it operates with kind of HVAC and HVDC. So a combination that'll be very interesting. I'll hand yourselves over now to our third presenter of the day, Adrian Coughlin. So Adrian is currently working as a client engineer in the engineering and asset management team in CIGRE. He'll be presenting on the HVDC for technology to be used for the Celtic Interconnector.
Thanks, Connor. Yeah, like Connor said, I'm working in CIGRE at the moment, but I spent just under a year working on the Celtic Interconnector project. So my role in the project was to assist with specification development. So the specifications were divided into 3 areas. There was the converter, the cable, and then the common. So the common would be project management and full system testing, but I'll be talking about the converter side of the project. Just see if I have control. Yeah, there we go. So yeah, I'll be going through with HVDC, the 2 types of HVDC there is, the differences between the 2 types and why in Celtic we chose one over the other, and then a quick overview of a typical HVDC compound. So firstly, I suppose, what is HVDC or where is it used? I know Gianni touched on it a bit there, but it's effectively transmitting AC power across a DC link through this converter station or a rectifier station, and then converting it back in the other end onto the AC network. So it's bidirectional. It can flow in both directions, and what it sets this power flow is the market. So the market dictates how the power flows. Again, something Gianni touched on there was the other alternative use for HVDC. It's called back-to-back HVDC, and this is where you join an AC network with another AC network, and they could be running at different frequencies, different voltages, but it's a safe way of connecting to AC networks, to asynchronous AC networks. So an example of this is Brazil and Argentina are connected with one of these back-to-back HVDC stations. So I suppose when we were choosing our converter technology for Celtic Interconnector, we chose a VSC, so that's a voltage source converter. But I'll talk about the other type of converter there is. It's called LCC, so line commutated converter. So a few of the reasons why we didn't choose this one or didn't go down this path. Firstly, LCCs have a higher reactive power demand. So that what that means is they consume reactive power in the place where they're connected, and they also use thyristors, which are controlled on a point on the waveform. So because of these 2 reasons, they have to be connected to a part of the network that is it's strong, as you'd say, so a strong part of the network, and that sort of reduces your flexibility or where you can select the connecting point. Another reason for it is more complex power reversal. So what that means is there's 2 cables joining both sides, a positive and a negative, and with LCC, the current always flows in the same direction. So if no matter what way the power flows, so the power could flow in this way, and the current will still be going in the same direction. So to reverse the power flow, you need to reverse the polarity on the cable. So this cable needs to be changed from positive to negative for the power to flow in the opposite direction. And this brings stresses on the cable. So it's a lot more instantaneous with VSC. It's an easier power reversal. So because of this, you have a reduced selection on cable types. It's more typical that you'd use what's called is mass impregnated cables. So they're sort of a chunkier cable, whereas with VSC, we're able to use XLP extruded cables. So these are what would be more common in the network at the moment. To push on to the VSC, so the other type of technology that is used in the Celtic Interconnector. Firstly, I suppose there's greater controllability when inverting the sine wave. So what that means is the two types of components that are used are transistors in VSC, or let's say thyristors in LCC and transistors in VSC. So transistors, it's easier to control them to create this waveform. So this is a crude version of what the waveform would be. There'll be thousands of these little steps to make the waveform. So it's easier to do it with VSCs. With the IGBTs, they're called, they're insulated gate bipolar transistors. But so that's one point. And also it's easier to control the reactive power. So VSCs have an inherent reactive power component or controllability, whereas LCC, you need to really compensate for this. The second point, because LCCs need this waveform to work, VSCs don't. So VSCs can be triggered at any point along the waveform, or if there is no waveform. So that means they have black start capability. So we heard Thomas saying at the start, EWIC has black start capability there. So that means if the Irish network did lose all the old voltage or lose power, all we would have to do is start a diesel generator that's in EWIC, we'll say, for example, start up the house load, start up the cooling for the converter station, and then as long as France has power, we can use that to start our network. Another point there, because this sine wave is smoother, in LCC it'll be a lot more jagged nearly, so there's a lot more harmonics associated with it, and these harmonics are hard, or they sort of damage transformers, so you need to get a transformer that is able to take these harmonics, and you don't need that so much with VSCs, so you can get a more standard transformer, something that is used in normal AC transmission systems, so that's more reliable, has more spares probably, and is usually cheaper as well. So, and the last point there, reduced HV equipment. So because there's less harmonics, because you don't need all this reactive compensation, this is reduced equipment needed, and also a reduced footprint on site, so a smaller site that you need. So then just the last point to run quickly through what the HVDC compound would look like. This is EWIC, like I said, that's joining Ireland and Wales. It's a smaller system, 200 kV cable, whereas in Celtic we're using 320 kV DC cables. This is 500 megawatt, whereas EWIC or Celtic will be 700 megawatt. So you can see the DC cables come into this DC hole. This is where the terminations are. The valve hole, this is where the conversion or the inversion or the rectifying takes place. VSCs have their own reactors and filters to filter out any harmonics that are present, and also to provide compensation. And then they have the standard transformers, so just AC transformers into an AC bay and then out onto the transmission system. So yeah, that's really it there, Connor, and I'll take any questions at the end anyway. Thank you.
Yeah, good stuff. Thanks a million for that, Adrian. We'll plow on to the next one. Finally, to finish off, our fourth presenter is Yanis Corlu. Yanis joined RTA's Expertise Centre in 2016, where he worked as a cable system engineer on the Biscay and Celtic Interconnector projects. And he'll be presenting on the HVDC cabling to be used on the Celtic Interconnector.
Yes, hello everyone. So we can start with the first slide. So it's been discussed so we've been discussing of this interconnectors. I just want to quickly introduce use it first. Basically, the needs are well known. There need to transmit 700 megawatts. This is an important parameter which will help us size the cable system. In addition to those 700 megawatts, there will be also electrical losses that need to be covered, but that's minor. To help the converters to operate, we'll need telecommunication link, and also it's been said by Thomas for Eric, we will also monitor the DC cable link through several systems, DTS, DS, and FTTR. So it will help us assess the status of the cable link during its lifetime. So that was the need to help us design this cable link. We also have the lens of the project. So based on those needs and the state of the market, we decided to go for a 320 kV HVDC link with an XLP cable technology. By state of the market, I mean this is quite a large project. We need to have some suppliers able to provide enough cable in due time, and with how to say that, and cable design which is also robust enough, so it has been tested and is reliable. Yes. So a project with quite some competition. So for the cable link, the scope of the contract is this one. This is an EPC contract that will cover the supplies, installation, and the jointing of the cable system, and also the onshore civil works, the landfall, and the offshore operation protection. There will be also an EMR contract that will be signed with the EPC contract. That's it for the cable link. So we've seen this. So we've seen the cable link. So this is more or less for the HVDC part, more or less 570 kilometers of cable route with 500 kilometers of subsea cable link. We will have so 2 unipolar HVDC cables will be installed, and 1 FO cable for the telecommunication. We might have also, but this is optional, some FO cables for the monitoring aspect. So this is the HVDC link. Can move on to the next slide. What is a DC cable system? Just a quick introduction to that. Obviously, we will need terminations at the end in the converters. We will have underground cable and submarine cable. It's quite obvious as well. Those are unipolar cables based on an XLP insulating technology. We will need also joints so some of those joints, so rigid joints, river joints, and underground joints are built on site. We need those because of some installation limitations. For the land part, it's no, not yet. Sorry. We need those joints for the installation part. With that, we have limitations because of the installations of the weight of drums for the onshore part, and the cable laying limitation for the offshore part. And we also have factory joint builds in factory for the submarine part. So those are specific to the cable system. Now you can move on to the next slide. Just maybe an introduction to the cable by itself. So those are quite, I would say, easy. In the end, it's a bit more complex. So a DC cable is just a succession of layers which all have functionalities. You can just click. Each layer has a function. The connector is here to transmit the current. It's made up of copper or aluminum. Then we have the insulating part, which is composed of 3 layers, semi-conductive insulation. Here it's LP. We then have the metallic sheaths and the inner sheaths, which help for the water tightness of the cable, to transmit the short circuit current in case of failure, and also for mechanical protection of the inner part of the cable, so insulating layer, which is the most critical part. And then for submarine cable, because it's a submarine cable, we have armor and another outer protective sheath. This armor is here for the mechanical protection of the cable during pulling and laying. We can move on if you want. So, how to say that? So, we will sign a contract with a cable supplier that will have to produce a huge amount of cable, then install it and put it under operation. The main part of my job here is to work with this cable supplier to build a test program to be sure that what it will propose will be suitable for our needs. In order to do so, we will have several test phases. So first, the compliance test. So after the project award, we will have a compliance test that will be performed on prototype in order to demonstrate that what it proposed is okay for us. We will test all the aspects of the cable system, so mechanical properties, the electrical ones, thermomechanical, and everything. We'll build a test program with the cable supplier based on his technology and performed on prototype. Then we will validate the cable system, and the cable supplier will be able to mount to the mass production. During the mass production, we will perform routine and sample tests to assess that the quality remains the same during the whole production. So this production will be more or less in 2 years or 2.5 years. This is done in factories before the installation part. During the installation and after it as well, we will have the commissioning test that will be performed to check that the installation did not damage the cable system and that the accessories that are built on site are well fitted. And after that, once everything, we can say that we can take over the cable link. Obviously, those tests are based on international standards and CIGRE recommendation. And yes, the onshore installation will be quick on that. So the cable will be installed in ducts. Here you have a typical layout of cables. Yeah, so this is PVC ducts in concrete bank. So in red you have the DC cable, and in yellow the telecommunication FO cable, and 2 monitoring cables. Say that those were optional, but some cable supplier might propose it in order to perform the monitoring of the cable. From time to time along the cable route, you'll have some joints. Those are necessary due to drum limitation. You can't move 30 or 40 kilometers drums, and it's also needed to control the earthing of the cable screen. When you have a failure, you can have over voltage of the cable screen that can damage the other layer. So you need to earth it from time to time to control it. For the offshore part, so it was said that this was a 500 kilometers submarine cable route, which will cross the Irish, UK and French waters or exclusive economic zone. The Irish landfall will be in Clay Castle, and the French landfall will be in Cardenec. For the French landfall, it will be a trench length landfall. So duct will be pulled under the the beach, and the cable will then be pulled in those ducts. You can move to the next slide, and final one for the ocean installation. Just a quick explanation. So cable will be laid in by specific cabling vessels. On those vessels, you can also perform the jointing of the cable. So you can build the rigid joint. So this jointing is performed at the end of each installation campaign. So first you lay the cable, then if you can click, you have to protect it. So the cables are either protected by being buried in the seabed, or so for that you use plow for cutting tools, and you can also, and it will be done for Celtic, need to protect it with external protection, such as rock beam or mattresses. You have to do that when the soil is too hard. It will be the case for a large part of the Celtic the mine cable routes. So that's it for the cable part. Thanks.
Perfect. Thanks a million for that, Yanis. That was very good, very interesting presentation. So I know we're running a little bit late now, folks, but I think I'll hand over to Nicola now. I'll just let you do the audio, Nicola, and you can sort the Q&A questions from the Slido.
Yes, thank you, Connor. We have a few questions. Thank you to everyone who posted questions on Slido. I have combined 2 or 3 of them about the cables as a first question for our presenters. The first question I would say is, are all the portions, all the sections of the cables monitored? And how to identify a given faulty section? Maybe Thomas or Yanis can answer to this part. The questions were popped when Thomas was presenting, so as you want, guys.
Yeah, I could probably address the first portion of that question anyway. Yeah, so unfortunately, the cable route isn't currently being monitored, just to the limitations of the fiber type we're using for the system. As I was saying, I think it's maybe 30 or 40 kilometers from the Irish side and 25 from the UK side of the submarine cable is monitored. So going forward, we are currently speccing a new system and what we're kind of expecting as part of our DTS system upgrade. So we are planning on increasing that range. To what degree, I'm not 100% sure, but we are hoping to get considerably more coverage going forward for our upgrade.
And are you today able to identify a small portion of cable that is faulty, or is it more like 1 or 0?
Yeah, no, it's quite precise. Once you have a temperature spike, it'll give you a pretty precise location. So even just recently, we had a faulty fiber on the system that we had to switch over, and it did give us a temperature spike, and it gave us a pretty precise location where we could pinpoint where we thought there was a fault in the fiber, and we were able to switch over to a spare. Okay, and as you answer really precisely and really fast, one last one for you. Is it a predictive maintenance or a reactive maintenance when there is an issue? Are you able to predict something? Well, with the converter stations, I think there is possibly more of a predictive maintenance. And then with the cable, it's all about just being proactive in terms of trying to minimize any risk to the cable, being aware of what shipping routes are passing the cable, whether there's going to be potential for export cables crossing the route, getting in crossing agreements, and doing our monthly route drives and just spotting any issues, whether it's changes in road surfacing or contractors who are working in vicinity of the cable who weren't aware of safe working practices. It's always, from the cable perspective, it's preventative rather than reactive.
Thank you very much, Thomas. We have another trendy question on the Slido. Could you speak a bit more? I don't know who it is addressed to, but I think it popped up when Gianni was speaking, probably, about the issues of HVDC being connected to the AC grid with regards to stability issues.
Yeah, I'll try to answer to this question. This is my topic of thesis, so it will be after 2 years of work. But till now, we can notice that if not proper HVDC control is implemented, we can notice that it affects badly the AC grid. Like for example, if I want to damp those oscillations I showed in some of the in the last slide, I can put a POD, a power oscillation damper. So HVDC contributes to the enhancement of our system stability. However, if the POD doesn't have the proper gains and proper control, fast control, and connected to the proper converters, and if not everything is working as expected, you can imagine directly that HVDC can destabilize the system or lead it to a worse state after injection of power. So that's why we need to really tackle this question of AC-DC interactions. Another problem, like I can add, is due to power electronics. You have there is a study I saw not long ago that shows that we can have, for example, a nuclear power plant. I don't remember where in the world, but there was a study showing that a nuclear power plant can go into oscillations even due to power electronics nearby it. So if you have power electronics near a nuclear power plant, it can go into oscillations, and this is called resonant oscillations of a nuclear power plant. So all these issues need to be tackled.
Thank you very much, Jenny. Maybe one last question, Connor, if we have some time for that. It's a question that is addressed directly to Yanis about the commissioning tests for an HVDC link. What are the typical commissioning tests for such a link, Yanis?
For the DC cable by itself, you just fuse the cable and you put it under tension around the voltage, so 145 U0 for 1 hour. The main part of the commissioning will be on the converter side. There will be trial operation. You should mostly perform by the converter part. There will be a 3 months trial period, I guess, at the end, just to be sure that everything is fine. You need to control everything. So for the cable, it's quite easy. For the converter, it's much more complicated. But still, you need to have both contract entangled there for that.
Okay. Connor, do I have a green light for the last one, or is it?
Yeah. Go ahead, Nicola. Yeah, we'll get one more in. Okay.
Maybe the last one is about the size of the link. The island aims to install 30 to 40 gigawatts of wind power in the next decades. Is a 700 megawatt link a good size for exporting the power from wind farms? If we have someone to take that one.
I suppose I'll try to field that one there.
Thank you.
There was considerable studies done, like the 700 megawatt figure wasn't just pulled out of the sky. There was considerations done about what the capacity of the network would be, and about what future alternative interconnection there is. There is more interconnection coming between Ireland and England in Greenlink as well. So between that, and I think that's 500 megawatts, if I'm correct on that. So serious decisions or serious discussion was made, and there comes probably a point, that price point where it's, while feasible, it may not be economically effective to go higher than 700 megawatts. So it would be considered, it would have been considered, the amount of wind and offshore wind that is coming, but I couldn't fully tell you why, or precisely why the 700 was chosen.
Okay.
May I add something about that?
Okay.
You can also think of what happens if there's a failure of your link. You'll have 700 megawatt of that you need to deal with, and for the Irish network, it's too much. It would be too much to go above this value. So you must see that on the other side. So what happens in case of failure? For the French part, it's something like 2 gigawatts that you can lose without putting the French network in the attention, but for the Irish part, it's much lower. You can't have too much interconnection.
Thank you very much. We had questions for all of our speakers. Perfect. Connor, I let you for the closing remarks. Take the lead. Thank you very much.
Yeah, cheers to that, Nicholas. And big thanks to all the speakers today. The slides are all very good, very informative, and it was extremely interesting and I suppose very topical series of presentations, given how Celtic Interconnector has taken off these days and how important it is to kind of link the Irish power system to the rest of Europe and the French system properly without the dependence on Great Britain. And again, thanks to everyone as well today who has signed on for the call for the webinar. I really appreciate you taking the time. And again, if anyone on the call is a young engineer or early career engineer or professional who hasn't joined the CIGRE NGN for either France or Ireland respectively yet, I'd advise you go and do so because it's very useful. We send out newsletters, we have events like these, and it allows you to access a number of resources that will help you kickstart your career or help develop your knowledge a bit more that you mightn't have got otherwise. And again, yeah, just big thanks to everyone for joining on, and hopefully we'll catch you again soon in the future.